Hello, everyone. Welcome back for session Monday B at the 13th International Conference on Computational Photography in the year of 2021. And my name is Bo-Xin Shi from Peking University, the chair of this session. And in this session, we have 3 paper talks and 1 physics object abstract talk. Now let me introduce the first talk. The title is Convolutional Neural Opacity Radiance Diffuse from Professor Jing Yu's group at Shanghai Tech University. Now we will play the recorded video presented by Haimin Luo.
Hello everyone, I'm Haimin from Shanghai Tech University. Today I will present our recent work, Convolutional Neural Opacity Radiance Diffuse. This is a joint work with Anpei, Qixuan, Bai, Mingye, Lanxu, and my supervisor, Jing Yu. I'd like to first give a whole message of our work. Our convolutional neural opacity radiance diffuse aims to produce high-quality free viewpoint rendering of fuzzy objects from real-captured RGB alpha photographs. Then, given novel camera poses, we can directly render high-frequency detailed RGBA images, as shown in the right side of the slide. Thus, it can enable various applications such as background adjustment. Opacity estimation and rendering is a long-standing problem in computer photograph community. To render free viewpoint opacity, Matusik proposed an image-based visual hall called IBOH that uses images with alpha matte at sample views, and then set out to interpolate RGB and alpha at novel views. Such straightforward method can reduce aliasing near the boundaries, and it requires a high-quality 3D models. In contrast, most recently, NOPC only requires a relatively sparse set of samples with coarse 3D geometry. Another notable exception is NERV, which implicitly models the radiance fields and the density of a volume with a neural network, and then use a direct volume rendering function to synthesize novel views. However, such pure ray-based rendering schemes are failing to recover high-frequency surface, such as fur. We attacked above challenges and propose a novel scheme to generate convolutional neural opacity radiance fields for fuzzy objects. More specifically, given multi-view RGBA images, we use SFS algorithm to infer proxy geometry for efficient ray sampling, which utilizes the inherent silhouette prior along the rays and encodes the spatial information across the image plane. For each sample point in the volume space, the position and the direction are fed into an MLP-based feature prediction network to represent the object at a global level. We then concatenate nearby rays into local feature patches and decode them into RGB and alpha patches with the convolutional volume renderer. We train the convolutional volume renderer with 3 generation loss and 1 discriminator loss. An adversarial training strategy is used on the final output to encourage the fine surface details. In the reference period, we render the entire image at once rather than per patch rendering. We then introduce the ray sampling technique. Unlike NERV predicting pixel color by integrating in a low-dimensional color space, we instead perform a novel volumetric integration scheme to generate a per-patch hybrid radiance and opacity feature maps to enable more effective radiance field learning in a patchwise manner. That is, we use a MLP network to extract the radiance feature and density for each sample point. Then we weighted blend the radiance features of each ray with the estimated alpha of the sample points as the ray feature. Finally, we concatenate nearby ray features into local patches for the following convolutional rendering. After feature patch construction, we can obtain view-dependent radiance feature map and opacity feature map for each patch, which will be fed into convolutional volume renderer. We note that the original NERF fails to recover the high-frequency details of fuzzy objects. To address this issue, we introduce a convolutional volume renderer scheme for view-consistent radiance and opacity rendering by utilizing the spatial information based on the per patch features which encode the characteristic of appearance and opacity. Note that we aim to achieve view-consistent rendering. However, the local receptive field of convolutional neural network may introduce view inconsistency. Thus, we design a lightweight renderer network to replace the last fully connected layer of the original NERF network and decode the feature maps into radiance and opacity. Our renderer consists of a radiance branch and an alpha branch with U-Net-like architecture. Note that in our radiance branch, two downsample-upsample blocks are adopted to generate fine-detailed texture output, while only using a single downsample-upsample block in our opacity branch to preserve view-consistent alpha output. Since the input feature maps suffers from incomplete integration near the boundary regions, which is critical for fuzzy objects, we therefore adopt the gated convolution in the U-Net for both radiance and opacity branch, which enhances the denoising and image completion capability of the network. The renderer predicts foreground radiance and corresponding alpha. Then we complete the foreground with the background to get the final rendered images. For the data capturing, we designed a spectral system for fuzzy objects. The system consists of a precisely controllable step turntable placed in front of the green screen and 6 cameras facing towards the objects. The fuzzy object is placed on the turntable. For weak data, we use a transparent support covered with soft light fabric to support the objects and place them on the turntable. Then we insert a LED light bar into the support to make the soft light fabric lit. Before capturing, the cameras are adjusted to overexpose the soft fabric part, which will reduce the shadow of the captured images and provide a clean white screen. Then to obtain alpha without loss of rich details from fuzzy objects, we apply both 3D keyer and deep learning-based matting algorithm. Firstly, we key out both green and white from the image to extract a preliminary foreground mask. Then a tri-map is generated from the mask using erosion and dilation operations. Finally, we apply context-aware matting to predict alpha matches and foreground images, which combines the benefits of local propagation and global contextual information and perform visually much better on interactable data like curry hair and air bounce. Here we compare our ConvNeRF with the state-of-the-art image-based rendering and neural rendering techniques. We can see that in the video, the IBOH suffers from ghosting and aliasing due to the input fields are in uniform sampled. The point cloud-based method NOPC can partially generate smooth textural details with sufficient training images, but still suffers from blur due to interpolation between the features projected from the discrete spatial point cloud. The NeRF can preserve low-frequency components, but fails to recover high-frequency details due to the limited representation ability of the MLP network. In the FIR region, there is noise caused by insufficient samples on both ray direction and the ray resolution. It should be noted that NeRF fails to generate correct alpha on our challenging real hairstyle dataset. In contrast, our ConvNeRF is able to reconstruct fine texture and geometry details and present sharply visual results. As for future work, currently our method relies on accurately calibrated camera poses and precise alpha matches. It is interesting to extend it to the in-the-wild data, which are captured by smartphones and consist of a complex background. Also, our model now takes several seconds to render a novel view. It is interesting to combine our method with other existing cache-based methods to achieve real-time rendering. And it is a challenging but really meaningful work to extend our method to dynamic scenes. Finally, we will collect more hairstyle datasets for further research. Thank you very much for your attention.
Okay, so this is a very interesting presentation. So there are some questions online, and people is interested in how many views you require to achieve the good quality reconstruction.
Well, actually, in our experiments, it usually requires 200 to 300 views for a case. Yes.
Okay, so I have a question. So I'm very interested in the real data capture system. You know, this kind of high quality multi-view RGB alpha data is very important for your system. I see for the weak data, there is an LED bar inserted. It seems like inserted inside the object. Why this is needed and how it contributes to capture better quality of ground truth alpha?
Yes, actually, it provides a wide screen, and it can help us make a foreground mask to mask out the actually yes, it helps us to focus on the hair object itself, and actually we can take it with the green screen. We can get a coarse hair mask, and then we can get a tri map of the hair, and then we can feed it into the matting algorithm, and then we can get a alpha mat for the hair itself.
So when you capture the wig, how do you put the LED bar? Is it around it or somewhere very close to it?
We actually insert it from the bottom of the fabric.
Okay, but then it means that the fabrics is somehow are translucent or partially transparent. So for other objects, like you have the wolf or this kind of opaque objects, how do you put the LED bar, or do you still need it?
No, for other objects, we don't use the LED bar, and we just put it on the turntable, and we can and just capture them. Yeah.
Okay. Okay, so let's move to the second paper. And the title is Non-Rigid Shape from Water. This is from Professor Convolutional's group in Kyoto University. And now we will present the recorded video presented by Mengyu Jennifer Guo.
Hi, I'm Mengyu Jennifer Guo, and I would like to present our work on reconstructing the whole shape of a fluorescent fish. This work was conducted at the Computer Vision Lab of Kyoto University with Liu Kawahara, Shohei Nobuhara, and Convolutional. In this work, we introduced a novel method for recovering a holistic, dense 3D shape of a deformable dynamic object in water. We achieved this by introducing a novel method for estimating dense underwater 3D scene flow while also accounting for underwater light scattering. Our method only requires a single camera and a single light source, and we do not assume orthographic projection on either. To realize this simple setup, we derive a novel light source calibration method that accounts for perspective projection and refraction. Recent works have shown that path length dependent near-infrared light absorption in water can be leveraged for underwater 3D reconstruction. These methods strictly assume orthographic projection and directional light, which inevitably limits the field of view and thus the overall utility of the methods. Other past methods on underwater shape recovery are only applicable to either static objects or frame-independent dynamic objects. In other words, we could only reconstruct the shape of underwater objects as frame-wise isolated geometry. To the best of our knowledge, our work is the first to recover a consistent and consolidated 3D shape of a dynamic, non-rigid object in water by just passively observing it as it freely moves. In our work, we take advantage of path length-dependent absorption of near-infrared light. Light absorption in clear water can be modeled with a Beer-Lambert law as a relation between transmitted radiance and incident radiance, where incident radiance exponentially decays as a function of light travel distance. Here, alpha is the wavelength-dependent absorption coefficient. We consider a perspective camera and a point light source, observing and illuminating an object through a flat refractive medium. Without loss of generality, we adopt the axial camera concept to simplify the pinhole camera model. That is, the optical axis is perpendicular to the flat housing of the camera. In this figure, an incident light travels to a surface point of depth d and reflects and travels back into the camera. The total light path length in water will be this. For a surface whose reflectance function can be factorized into spectral and geometric components, the intensity of the light captured by the camera becomes like this. By capturing the same surface in two distinct near-infrared wavebands from the same viewpoint, light path length in water can also be obtained by taking the ratio of these two equations. To recover the depth of an underwater object, we need to know both the positions of light source and camera with respect to the housing. For this, we derive a novel camera light source calibration method. We assume the intrinsics of the camera is calibrated beforehand. To calibrate a light source, we first immerse a reference object, such as a checkerboard, in water and measure the depth of the points on it. As the bispectral imaging principle provides the total light path length in water, we can obtain the distance from each reference point to the light source in water. Therefore, the possible ray direction in water from a reference point form a cone, and a family of rays form a conical frustum in the air. We can express this constraint as this. Here we denote RS, CS as a light source position in the camera frame. We can linearize this constraint using RS squared and ZS squared. By stacking 3 or more constraints from multiple reference points, we can find the light source position as the intersection of the corresponding frustum. This initial point light source position can be further refined by this, so that it satisfies the Beard-Lambert law for the observation of the reference points. Once the camera and light source are calibrated, data each pixel from an arbitrary underwater scene taken with a calibrated image system can be computed by minimizing this. For an object observed in a scattering medium like seawater, we model the light captured by the camera as a sum of direct transmission, backward scatter light, and forward scatter light. We subtract the contribution of backward scattering by using an image of a uniform sheet captured at a single distance, roughly at where the object would normally be. We assume the contribution of forward scattering can be approximated with convolution to the direct component. Once we have the initial estimate of both scattering parameters and depth, we can further refine them in an alternating fashion until convergence. Up to here, we have established perspective shape on water with scattering, but for each frame independently. To recover the holistic shape of a non-rigid object dynamically moving in water, we recover dense underwater 3D scene flow and use it to integrate per frame reconstructions. We assume that 2D optical flow across frames can be computed using a regular 2D optical flow method of choice. For robust optical flow estimation, we capture RGB data. As frame-wide 3D points are estimated by using 2 near-infrared captures from the same viewpoint, we can compute dense 3D scene flows across multiple frames in water by connecting recovered 3D points according to the estimated 2D optical flow vectors. As an object moves and deforms from frame T to frame T plus 1, given the estimated 3D scene flow, we employed the embedded deformation model to represent the non-rigid transformations for each pair of consecutive frames as a combination of a global rigid and patchwise local deformations. The points in frame T can be transformed into frame T plus 1 by first applying global rigid transformation, then local deformations. Once we have the initial estimates of all deformations, we can further refine them globally by enforcing the similarity of local motions and the fitness that maintains the fidelity of the original scene flow. The entire objective function is like this. Here, the last term is used to encourage as many corresponding nodes as possible. Given a non-rigid deformation from frame T plus 1 to frame T, we can integrate the points in just 2 frames. Here we set frame T as the canonical frame. For the points in frame T plus 2, we first estimate the non-rigid deformation between the points at frame T plus 2 and frame T plus 1. Since we have already estimated non-rigid deformations from frame T plus 1 to the canonical frame, we can combine them to establish the 3D scene flow between frame T plus 2 and the canonical frame, and then estimate the non-rigid deformations between them. By incrementally integrating 3D shape while accounting for non-rigid deformations, we can reconstruct the complete or fuller 3D shape of the object. Finally, we can further refine all transformation parameters for different frames to make them agree with each other by minimizing the gaps between the overlap areas, just like bundle adjustment in multi-view reconstruction. We built an imaging system consists of a point source and a custom-built multi-wavelength camera for video rate capture. We optionally use additional 3 texture light sources, each placed with an RGB bandpass filter in front of it, to capture more uniformly lit texture information. Here are the results of rigid objects in motion. These results showed that our method can accurately recover the complete shape of the objects in water. Here are the results of dynamic non-rigid objects. We can observe that our method successfully reconstructs the rest-shaped geometry of the deforming objects in water. Here are the results of lived creatures in real-world water of different turbidity taken from a river, a lake, and an ocean. Our method successfully integrates all the frames to obtain an accurate and fuller 3D shape reconstruction despite the scattering by water. To conclude, we believe that our novel method for integrated non-rigid shape recovery of dynamic objects in water opens a new avenue of applications for underwater 3D sensing. Thank you.
Okay, now let's move to the Q&A session. So there are some questions from the audience online. So the first question is how the reflectance of different objects influences the result, like the specularity.
For the depth recovery, in the previous bispectral shape of water method, they investigate several classes of materials, including wood, leather, metal, and spectral, and they found that the difference of the reflectance spectrons is usually very small in the near-infrared range. So in our work, we simply follow this and assume that the per pixel albedo can be approximated to be invariant in this range as well. So that means in our depth recovery process, the reflectance function of the object surface can be arbitrarily, because as the geometry and spectral components can be eliminated during the estimating the light path length in water. But for the 2D optical flow estimation, the objects with Lambertian surfaces with the view dependent specularity would have higher accuracy.
Okay, so there's another question. So why do you use the near-infrared light for the depth estimation?
We use near-infrared light for the recovery is because in the previous shape of water methods, they did some analysis and they found that we should make the difference of the attenuation coefficient to be as large as possible to achieve higher reconstruction accuracy. And as the amount of light absorption changes quickly in the near-infrared range, so we chose the wavelength within the set that can be per cases of the shell near-infrared filters.
So the last question, so how about the reconstruction speed? Can it reconstruct video in real time?
Well, our custom-built multi-wavelength camera is built by time slicing using a spinning well. So theoretically speaking, this is not the one-shot imaging system. as the 5 wavelength images are not consecutively captured at once. Well, in practice, the time difference between the different wavelengths would cause some drifts in different wavelength captures. But in our work to achieve a higher reconstruction accuracy, we account for this drift by interpolating the drift time relationship using the estimated optical flow. And we are not aware of any other camera that can capture the single viewpoint, multispectral, and real-time video.
Real time.
Although, yeah, it would be great if we can have a custom build, for example, a MVIR system with sufficient fidelity.
Okay, so thank Jennifer. So I think I will stop here due to the time limitation. And there are still some questions on the live chat on YouTube. Maybe you can follow up with the audience later.
Okay.
Thanks. So before I announce the next talk, there are some announcements about the keynote speaker. To those who are not familiar with ICCP, computational photography is an intersection of disciplines involving imaging, optics, sensors, signal processing, computer vision, and graphics. We will seek here creation of new photographic and imaging functionalities and experiences. We want to go beyond exclusive desperate camera and image processing technologies. So we are very happy to have two keynote speakers in our Monday session C and session D. I think it will happen like 3.5 hours later. The first keynote speaker is Professor Ionila Elda from Weizmann Institute of Science, and she will give us a presentation entitled Imaging from Compressed Sensing to Model-Based Deep Learning. And later we will also have another speaker, Professor Joseph Shaw, who is a distinguished professor from Montana State University. Please follow up our conference program, and you're welcome to join these two great talks. And I'm sure we will learn a lot from these two keynote talks. Okay, now I will stop my screen share. Now let's move to the third talk for this session. This is a abstract talk, physics optics abstract talk entitled Information Analysis of Imaging Through Highly Diffuse Media from a team of University of Glasgow. Now we will present the recorded video presented by Jack Radford.
Hello, my name is Jack Radford, and today I'm going to talk about information theory analysis of space-time measurements and the limits of diffuse imaging. So our vision is to move to optical medical imaging technologies and away from bulky MRI instruments that take up entire rooms in hospitals, or instruments which use harmful ionizing radiation such as CT scans and PET scans, and replace some of their uses with a medical imaging technology which uses visible light or near-infrared light to image inside non-invasively the body and the brain. So the issue with using near-infrared light is that the photons are highly scattered inside human tissue. So compared with X-rays, where X-rays photons can travel through human tissue relatively unimpeded, regions where there is bone and the photons are absorbed cast a shadow onto some photosensitive screen that gives us a really nice image of an X-ray. However, when you use near-infrared light, then even though the photons do interact with absorbing regions, then because every time they're scattered, they randomize their propagation direction, then by the time they're re-emitted from the tissue, they've lost a lot of spatial information about hidden absorbers. So a useful quantity that we can define to quantify how diffusive a material is in terms of the number of transport mean-free path lengths that a photon experiences. And this just quantifies the average distance that a photon can travel before its initial propagation direction gets randomized. So in fact, there is some photons, a very small probability of photons, which travel through tissue without interacting. But for those, we need to separate them from the ones which have scattered. And to do that, we use a timing technique. So we have a time resolved detector here, which is a SPAD array. and SPAD stands for single photon avalanche diode. And these are detectors which are sensitive enough to detect a single photon, but they're also they have timing capabilities to record when that photon arrived at the camera. So they can time a photon from one side of material to another, and clearly the ones that arrive first will be the ones that have the shortest path length, and therefore the pixels which have very short arriving photons, those ones can reproduce an image similar to the regime of X-rays. However, these ballistic photons, as they're known, they are plentiful when we're in the regime of about 10 transport mean free paths, which corresponds to less than a centimeter of tissue. But if we want to image through around 5 centimeters of tissue, then we're in this regime above 80 transport mean free path lengths. And we'd only see one of these ballistic photons per age of the universe. And instead, all of the photons we're seeing at the camera are these diffuse scattered photons. And this study aims to look at how best to capture the information of those diffuse photons in order to reconstruct images. So the numerical simulations used in this study are based on a real experiment, which was published in Nature Photonics by the group in 2019. And it consists of 2 polyurethane slabs, which have optical properties similar to human tissue. And between those 2 slabs is a hidden absorbing piece of black tape in the shape of an X. And the task is to reconstruct the image of the tape. So in the simulation, we can change parameters such as the thickness of the material or the object which is hidden in the material. And for thin materials, we can see that if we just look at the pixels in space, you can almost see the shadow of this hidden object. But as we move to very thick materials, it becomes a diffuse blob. And as we change this object, then the diversity of the image in space decreases, and actually we only see the same sort of blob every time. Whereas if we look in time, actually the propagation time for a photon to go through a thin material is similar for every photon that goes through, because they have less chance of scattering. Whereas for a very thick material, then every photon that goes through the material has a slightly different time of arrival at the detector, depending on how many scattering events happened in the material. So it has a broader distribution of arrival times, and actually the diversity of the distribution for in time for thicker materials is what we use to reconstruct the image. So to quantify the amount of information that we have in space first, we use Shannon entropy, which quantifies the the expected reduction in uncertainty for a random variable. And in this case, our random variable is the number of photon counts that we expect to see at a given pixel. So if we take the center pixel for these 3 different hidden objects, then they'll have 3 different number of photon counts that we're seeing. So if we do this for 1,000 different hidden objects and plot this as a distribution, we can see that the broad distribution would indicate that we have high entropy and therefore high information about the image in this center pixel. But at a pixel which is further near the edges, this has a lower diversity in the values that it could have for a number of photon counts. So therefore it contains less information. Similarly, if we take just the center pixel and we look at the time resolved information, then for photons which arrive at early times, then we see less diversity in the number of photons. So you see a narrower distribution. Compared with the later arriving photons, we see a bigger distribution in the number of photons for every different given example. So that would indicate that there is more information at these later time bins. And actually, if we take every time bin and plot its information, going to thicker materials, that total information increases, which would support the argument that actually, as we go to thicker materials, the information resolved in time gets greater. So this is said again in a different way with this graph on the right, where we increase the transport mean free path lengths experienced by photons, and the entropy or information in bits increases in time, but it decreases in space, since those blurred images that we get for every different object become more and more similar, and therefore the diversity decreases as we go to thicker and thicker materials. But if we resolve in both space and time, that's where every pixel in the detector has the capability to resolve in time, then we actually see orders of magnitude more information. However, we're going all the way out to 1,000 transport mean free paths here and still seeing information. But that's because I've given each measurement or each simulation the same number of photons to use. But we know already that the number of photons is exponentially suppressed as we get to thicker and thicker materials. So when we take that into consideration, along with short noise, then we can actually see that no matter which domain we choose, the information drops off just over 200 transport mean free path lengths. And this is for some practical values. So like 10 milliwatts of laser power, which is safe for using on the skin, and 60 seconds acquisition time, which is quite reasonable. So we'd expect to see information beyond about 12 centimeters of human tissue, which is quite exciting. And again, the blue here is the space and time resolved information. It has orders of magnitude more information. So in terms of image reconstruction, we can simplify the problem to a linear forward operator, where the targets are all of these hidden absorbing objects, and the measurements could be in space, in time, or in space-time. And we find the forward operator by this dot product, and then we can then find the inverse operator, which is what we're interested in, because that allows us to operate on the measurement that we see at the detector and reconstruct the target image. So to do this and get the inverse operator, we have to do a pseudo-inverse, and this is ill-conditioned, and therefore it's an ill-posed inverse problem. So what I'd like to do is compare how ill-conditioned this pseudo-inverse is when we have space data, when we have space-time data and time data. So to quantify how ill-conditioned something is, we use condition number, and this uses a singular value decomposition of the linear transform that we found into its singular vectors, which is the basis functions that we're going to use to build up our image. And these basis vectors are weighted by their singular values, similar to eigenvectors and eigenvalues, where the maximum singular value corresponds to the most important singular vector. So if this ratio is around 1, then it indicates that we have quite a stable inversion. But as this increases, we're more and more unstable to slight noise perturbations in our measurement. So in blue, again, we can see space-time has the lowest condition number, whereas space and time become quite ill-posed around 50 transport mean free path lengths. But the difference is clearer with an example. And when we have a ground truth, which is the image of this G, clearly the basis vectors we found when we use only space domain data gives us nice images. But when we add a little bit of noise, because it's ill-conditioned, this means that a small amount of noise in the measurement gives us a completely different solution, which is far away from the ground truth. The time is actually better conditioned. However, it's lower rank, so there's not as many basis vectors in which we can construct a solution in the first place. So again, it just gives us rubbish because it doesn't have enough basis vectors. And when we have space-time, then we can actually see it's robust to noise because it has resemblance of this ground truth image in the dark blue here, which is a perfect indication that it's reducing the ill-posedness of our inverse problem. So in conclusion, there exists information in diffuse photons. For practical acquisition considerations, such as 10 milliwatts power and 60 seconds acquisition, you can expect to still see information through around 12 centimeters of tissue. The condition number indicates that when we measure in both space and time, this reduces the ill-conditioning of the image reconstruction, which makes it less sensitive to errors due to noise, and therefore a more accurate image reconstruction. And future work would be to quantify and disentangle the independent information from the mutual information between these space-time and space-time domains, so we can actually quantify exactly how much extra information we get from resolving in these different domains. So thanks very much, and I look forward to your questions.
Okay, very nice talk, Jack. So let me first ask one question. So I like the analysis of the inverse problem. You use a very simple model to verify the proposed information series that is like multiplied by the inverse matrix. Have you ever tried to add some regularization term to your inverse problem to see how this affects the results?
Yeah, so there is already a more complex regularized inverse problem, which was published previously by the group in Nature Photonics, the title of which is Computational Time-of-Flight Diffuse Optical Tomography. And for this study, we wanted to not be biased in the image reconstructions due to regularizers, but instead look very objectively at the amount of information that we can transmit through the material, so without a regularizer, because a choice of a prior or a choice of regularizer can dramatically affect the reconstructions.
Okay. Okay, thank you. So there is another question online. So is there a relationship between temporal resolution and information? Does sampling finer help?
Yeah, that's an interesting question as well. And again, that was addressed qualitatively in that same Nature Photonics paper I mentioned before. And it seems like it might help because you do have, technically you just have more information, the more time bins or the more pixels that you have. The more interesting question though, I think, is whether those time bins are just repeated information or whether it's actually new independent information. So if you have a very blurry image, having much, much finer pixels is sampling the same blur. So from neighboring pixels don't have as much new information. So actually the position of the source and position of the detector can change this. And maybe the idea that if you have a blurry image, sometimes taking a step backwards can be more informative to look at things from a wider field of view. So in the same way as time domain, you could very, very finely sample this blurred diffusion curve, but actually maybe even having more samples or moving your detectors in a place so that they sample the time of flight of the photons in a much further, where the pixels are much further apart, might actually give more new independent information. But yeah, there is a hint that finer sampling can give better image reconstructions.
Okay, so thanks, Jack.
Thanks.
Now let's move to the last talk of this session. The title is Spectral MVIR, Joint Reconstruction of 3D Shape and Spectral Reflectance. So this work is from Professor Okutomi's lab at Tokyo Tech, and Chunyu Li will present his work in his recorded video.
Hello everyone, I'm Chunyu Li from Tokyo Institute of Technology. I'd like to introduce our work on spectral MVIR, joint reconstruction of 3D shape and spectral reflectance. This is a joint work with Yusuke Mono and Masatoshi Okutomi. This work aims to jointly reconstruct 3D shape and spectral reflectance, which are inherent geometric and photometric characteristics of an object. The spectral reflectance, which is defined in wavelengths, is inherent to the object and can provide much richer information about the object's surface compared with RGB values. Here we introduce the existing system of acquiring both 3D shape and spectral reflectance. We classify them into active lighting or scanner-based systems, SFM and multi-view stereo-based systems, and photometric stereo-based systems. However, these existing systems require expensive special equipment, such as a hyperspectral camera or a hyperspectral light source. A recently proposed state-of-the-art system called ProCam SSFM
has realized geometric calibration-free acquisition of the spectral 3D data by using an off-the-shelf RGB camera and LED projector. This system combines multi-view structure light and SFM techniques to estimate the 3D point cloth and the spectral reflectance for each 3D point. In this paper, we propose a novel method called Spectral MVIR for jointly reconstructing a detailed 3D mesh model and accurate spectral reflectance for each mesh vertex by fusing MVS and photometric stereo-based method. Next is our proposed method. We use a standard RGB camera and a smart LED bulb to capture multi-view input images. We exploit the smart LED bulb as our light source because it can emit several types of illumination with different spectral power distribution and thus can be used for multispectral observations. We fix the camera and the LED bulb on a plate and capture the images by moving the plate around the object while changing the illumination spectrum. Using the captured images, we first perform the camera pose estimation and the dense point cloud reconstruction by a standard SFM and MVS pipeline. Then we input the initial reconstruction results and the input images into proposed joint reconstruction. By solving an optimization problem, we can obtain the detailed shape, spectral reflectance, and light source positions. We next explain the joint optimization step. The optimization parameters are the power vertex 3D coordinate, power vertex spectral reflectance, and power vertex point light source coordinate. We can render multi-view images from optimization parameters. By minimizing the error between observed images and rendered images for all the camera views, we can optimize the parameters to get the correct result. The optimization cost function is composed with rendering term, spectral smoothness term, photometric smoothness term, and geometric smoothness term. Firstly, the rendering term evaluates the error between observed image and rendered image for all camera views. The rendered image is the product of RGB albedo, shadow, and shading. First, the RGB albedo can be modeled as the product of the spectral reflectance of the object, the spectral power distribution of the illumination, and the power spectral sensitivities for 3 channels. Then integrate over the visual spectral range, we can obtain the RGB albedo. For spectral reflectance, we approximate it using a linear combination of a small number of spectral bases. Then covering the spectral reflectance of a vertex is equivalent to estimating the weight vector, which has few unknown parameters. Next, the shadow and the shading are calculated from the geometric relationship between the light source position and the 3D vertex position. Only use the rendering term. The optimization problem is still ill-posed, so we include 3D additional smoothness assumptions. There are spectral smoothness term, which constrains the smoothness of the estimated spectral reflectance on spectral direction. The photometric smoothness term, which constrains the smoothness of the estimated spectral reflectance on spatial direction, and the geometric smoothness term, which constrains the smoothness of estimated 3D shape. Next is our experiment. We use a smart LED bulb as the light source. For capturing input images, we use a Canon EOS 5D Mark II digital camera. The spectral power distribution of illumination and camera spectral sensitivity are known in our system. Before conducting the spectral 3D reconstruction experiments, we select the best illumination set for spectral reflectance estimation using the spectral reflectance data of an X-ray color chart. The result is that we select the illumination set of LED1 and LED2 to quantitatively evaluate the quality of results. We performed simulation experiments using CG models. We create a ground truth spectral 3D model, which has ground truth spectral reflectance data for every 3D point. The ground truth spectral reflectance data is created by assigning the spectral reflectance data of the color chart to the 3D points. This video shows the ground truth light source positions and the estimated light source positions by our method. It can be confirmed that our method can accurately estimate the light source positions. This slide shows the qualitative comparison of the estimated 3D shapes. Left is the shape generated by OpenMVS that is used as the initial shape. Middle is the refined shape using our method, and right is the ground truth. We can confirm that more detailed shapes are reconstructed by our method. This slide shows the quantitative comparison of the estimated 3D shape on two CD models, Armadillo and Stanford Bunny. From this result, we can confirm that our method can provide better completeness and the accuracy compared with OpenMVS. This is a sampled spectral reflectance on the Armadillo model. We compared our method with the combination of OpenMVS shape and an existing image-based spectral reflectance estimation method. We can confirm that our method achieves closer spectral reflectance to the ground truth than the combined method. This is because the combined method does not consider the effects of shading and shadows on the spectral reflectance estimation. This is an error map for estimated spectral reflectance, where RMSE over all wavelengths is visualized for each 3D point. We can confirm that our method achieves lower average RMSEs compared with the combined method. These are the results of spectral and 3D relighting under different spectral power distributions and different light source positions. We also combine our spectral MVIR with ProCom SFM system, which is used a projector as hyperspectral illumination. Left shows the camera and projector setup, and right is comparison of the 3D shape between the results generated from ProCom SFM and our spectral MVIR. In this experiment, our method used the 3D shape generated by ProCom SFM as initial shape. We can confirm that our method can reconstruct more detailed surface than ProCom SFM, which is because the resolution of the reconstructed shape by ProCom SFM depends on the resolution of the projector. However, the resolution shape by our method depends on the resolution of camera, which is much higher in general. In conclusion, we have proposed spectral MVIR, which is a novel method for joint 3D shape and spectral reflectance reconstruction. To jointly optimize 3D shape and spectral reflectance, we have built a cost optimization framework based on a multi-view and multispectral rendering model, considering our image acquisition setup using a standard RGB camera and a low-cost LED bulb. Experimental results using both synthetic and real-world data have demonstrated the potential of spectral MVIR for the acquisition of a high-quality 3D model with accurate spectral reflectance. We can also demonstrate that our spectral MVIR can effectively be combined with the Procom SFM system that can produce a refined 3D shape.
Okay, so hello, Chunyu. So let me first ask a question from our audience online. So how the linear combination of the spectral term helps your system?
So the spectrum term means the spectral reflectance smoothness term. So because our inverse problem is a L post problem, so we assume that the spectral reflectance is smoothness on the spectral direction and the spatial direction. So we can put the spectral smoothness term to make the L post problem to a real post problem.
Okay, so thank you. So let me ask another question. So I like your setup, which is very compact and simple, because you have this kind of handheld camera, which is very close to your light source. But you know, for such a light source, in order to add the photometric constraints like the near light photometric stereo, you need to resolve a nonlinear optimization, right? You have something nonlinear term in your denominator. So have you ever considered you use a separate light source, which is can be detached from your camera? So this one can be far away as a distant light, so the photometric loss will become simpler. Will this like bring better results?
Yes, it's a good suggestion. I never tried it, but I think the results will not difference between the near light point light source and the you mean the far light position.
Yeah, because that's why we make the system linear. It will be easier to be optimized, like make the problem less ill-post, but it will not make the capture as compact or as simple as your method. It might require a larger space.
I think it's a good question, but I never thought about this. So thank you.
Okay, so I think there's another question. So what are some real-world applications that can utilize this kind of 3D plus spectrum?
Yeah, I think for some digital archive for some traditional I think traditional as traditional.
You mean some heritage or this kind of ancient buildings?
Yes, yes.
Okay. Okay, I think time is up. So maybe our people want to interact more, you can go to the YouTube live chat. Thanks to you again.
Thank you.
So now let's conclude this session, the Monday session B. We will have a long break, and after like about 3 hours, we will continue our virtual conference. We will go to Monday session C with our keynote speak, and followed by session D with papers and abstract talks, and again another keynote. Please go back later and keep an eye on our program online. Thank you for your attending. Thank you very much.